Hi everyone, my name is Adam Kotelewski and I will present our work on compositional convolutional neural networks. This is a new type of neural architecture that is much more interpretable and more robust to partial occlusion compared to standard deep networks. This is joint work with my great colleagues from Johns Hopkins University, Zhu He, Antiang Wang, Yihong Sun, Qing Liu and Alan Yuan. Let us first understand why partial occlusion is actually a fundamental problem in computer vision. As you all know, in natural images, objects are surrounded and partially occluded by other objects. What I'm showing here are images of partially occluded cars from the MS COCO dataset. Note that the occluders are highly variable in terms of their shape, texture, and position. In fact, in natural images, an object can be occluded by a large variety of other objects. Therefore, occluders can basically have any color, any shape, and occlude any part of the target object. And this occluded variability really makes the rather compact space of car images a lot more complex. In fact, the space of occluded car images is so big that it becomes practically infeasible to cover all possible occlusions in a finite training dataset. And therefore, the additional complexity due to partial occlusion makes it difficult for deep learning systems to generalize well under partial occlusion. We have conducted a number of experiments that demonstrate the lack of generalization of deep networks to partial occlusion. For example, here we train a deep network with non-occluded data and test with different amounts of partial occlusion. And as expected, we get very high results for non-occluded objects, but the recognition performance drops significantly the stronger the objects are occluded. Now, a standard approach to overcome a lack of generalization is to use strong data augmentation. So what if we train a neural network by superimposing other, unrelated objects on top of the target object? What we observe is that data augmentation helps in general, but the performance still drops significantly when the object is partially occluded. And note that data augmentation does not come for free. It increases the dataset size and also the computational cost and the engineering effort needed to train a model. So what we observe in these and a number of related experiments is that partial occlusion is really a fundamental problem for deep networks that needs to be addressed. I will now introduce our compositional nets, which will do a much better job at classifying partially occluded objects compared to standard deep networks. What I show here is a schematic illustration of a convolutional net. The input image is fed to a number of convolutional layers followed by a fully connected classification head. In the upcoming slides, I will refer to the feature activations of the last convolutional layer as feature tensor f. Note that the feature tensor has a height and a width that relate to the input image. Also note that a feature vector at a position p in the two-dimensional lattice of the feature tensor maps to a local receptive field in the input image. So the spatial structure of the input image is preserved in the feature tensor. This is an important property that compositional nets will take advantage of. The key idea behind our model is that we replace the fully connected classification head with a generative model of the feature tensor, p of f given theta. In particular, we learn a mixture model with mixture coefficients nu and corresponding mixture components p of f given theta m. Later on, you will see that each of those components will model a different 3D pose of the target object. Each mixture component in turn models the feature activations in the tensor f explicitly as a spatial composition of the individual feature vectors fp at different positions on this two-dimensional lattice of the feature tensor. This is very different from standard deep models, which typically reshape this tensor into a vector and therefore lose the spatial relations from the image. The likelihood of the feature activations is modeled as a mixture of von Mises-Fisher distribution. We explain this in more detail in our papers, but you can essentially think of this as being a Gaussian mixture model that is more easy to train. The basic intuition behind our probabilistic model is that we want to learn how the features will be activated for a certain object class. Because what will happen at test time is when objects are partially occluded, some feature vectors fp will have very different activation patterns compared to when the object is not occluded. And using this generative model, we will be able to detect and discard these feature vectors because they will have a low likelihood. This will enable the compositional generative model to focus on the non-occluded features for image classification. We can formulate the inference process with this probabilistic model as a neural network, where we first extract the feature tensor f using some backbone architecture. We then compute the VMF likelihood of each feature vector by convolving the feature tensor with the mean vectors of the VMF distributions, followed by a nonlinearity n that corresponds to the multiplication with the variance, the exponential function, and then the normalizing factor. Finally, we evaluate the mixture components and choose the component that can explain the image with the highest likelihood, which will give us the final classification score. As the inference process with the compositional model is fully differentiable, we can train it with standard backpropagation. But we need to consider that we have defined a generative model that we want to train in a way such that the training data has maximal likelihood under this model. Therefore, our loss is composed of 4 terms. The first 2 are just the standard cross entropy and weight regularization of the backbone. Those encourage the model to be discriminative. And then we add 2 terms that regularize the VMF likelihoods and the mixture models to have maximal likelihood. In summary, the overall loss encourages the model to be highly discriminative, but at the same time be generative in terms of the neural feature activations f for a certain class y. After training the model with our proposed loss, we can observe some very interesting properties of this model. What I show here are patches of training images that activate some of the VMF kernels the most. And what you can observe is that, for example, one of those VMF kernels focuses on wheels of motorbikes, whereas another one focuses on windows of airplanes and so on. So the VMF kernels turn out to become part detectors. And this is not surprising because they are trained to represent the data with maximal likelihood. And if a model wants to explain the data with maximal likelihood, it better learns to focus on those local image patterns that frequently repeat across the training data. A similar observation holds for the mixture components. Recall that a mixture component models the spatial feature activation patterns of the whole tensor big F. Therefore, when we train them to have maximal likelihood, we encourage them to focus on spatial patterns that frequently repeat in the training data. And as the spatial patterns of parts change the most when the 3D pose changes, each mixture component will start to focus on a particular 3D object pose. So overall, the inference process of compositional nets can be interpreted in terms of part detection and 3D pose estimation of objects. And note here that we train with class-level supervision only, and the interpretability evolves due to the maximal likelihood training. Now, while the maximum likelihood training encourages the interpretable representation of CompNets, our original motivation was to leverage the generative model to become robust to partial occlusion. Recall that compositional nets are generative models of the neural feature activations in the tensor F. Now, when some part of the object in the input image is occluded, the feature activations of the occluders will have low likelihood under the generative model that we have learned. Therefore, we can simply detect and discard those occluded features by finding those regions in the feature map that our model is not able to explain well. And we do this using a standard outlier model that is inspired by robust statistics. I will not give more details here as this is quite a simple process, but you can find them in the paper. To visualize the effect of the outlier model, I show the log likelihood ratio between the outlier model and the generative compositional model that we have just defined. These heat maps essentially highlight those regions of the image which the compositional model cannot explain well. And you can see that they very clearly and accurately localize the occluders in the image, despite the large variability of the occluders in terms of shape and appearance. And this occluder localization ability enables CompNets to be highly robust at image classification under occlusion, because they can simply focus on the non-occluded parts of the objects. What you see here are the classification results of a VGG model that is trained to classify vehicles from the MS-COCO dataset. If it is trained without occlusion, it does not generalize well. And using data augmentation, the generalization improves, but is still not very good. The compositional net trained without any data augmentation outperforms both models significantly. And note that this simply involves the replacing the fully connected classification head with our proposed compositional generative model. We also observed that the compositional net approach is very general and also applies to more advanced architectures like, for example, ResNet 50 or ResNext. we have seen so far is that we can classify partially occluded objects robustly with compositional nets. And what I will discuss now is how the model can be generalized to object detection. In our follow-up paper, we have also conducted a number of experiments that demonstrate that partial occlusion is not only a problem in image classification, but also a fundamental challenge for object detectors. What you see here in blue is the ground truth bounding box of the bicycle in the image, and in red, that's a detector result of a classic faster RCNN. In green, you see the result of a compositional net that has been successfully generalized to object detection. A naive approach for applying compositional nets to detection is to simply evaluate them in a sliding window manner. However, standard compositional nets do not perform very well, as illustrated by this orange bounding box. It shows that the compositional net would locate the airplane on the sky instead of the correct position, which is indicated by the blue bounding box. The problem is that compositional nets, as well as most other deep architectures, do not separate the representation of the object and the context explicitly. Now, if the training data is biased, such as in those ImageNet images that you see here, the model will learn that the blue background actually indicates the presence of an airplane. To resolve this problem, we changed the compositional net architecture such that the model becomes aware of the fact that an image is typically composed of an object and the context around it. In particular, we extend the feature likelihood for a feature vector fp to be a mixture of two terms, an object likelihood and a context likelihood. The mixture coefficient omega controls the relative weighting of the foreground and the context likelihood. If we choose it to be 0.5, we will retain the original compositional net. Whereas if we lower it to, for example, 0, the context will have no influence. In order to learn those likelihoods, we need to assign the feature vectors fp of the training data to either context or object. And we do this using a simple semi-supervised segmentation algorithm during training. In this image, I illustrate the influence of the context prior, omega, on the response map of the model. If omega is set to 0.5, and hence the context and the object model have equal weight, the model locates the object in the sky. This is illustrated by the orange bounding box. Whereas, if we reduce the influence of the context to 0.2, the maximum of the response map changes to the correct position, as illustrated by the green bounding box. These images show some examples of partially occluded objects that are detected successfully by the context-aware compositional nets that I've just introduced. Note that the context-aware models also have the ability to locate occluders accurately. Here we compare compositional nets and the faster RCNN on object detection of partially occluded objects on a subset of MS COCO. We observe that faster RCNN is not able to detect partially occluded objects accurately, even when trained with a lot of data augmentation. In contrast, compositional nets perform a lot better. In particular, we observe that deactivating the influence of the context improves the detection accuracy significantly compared to an equal weighting of the foreground and the context. We achieve the best results for partially occluded objects when the influence of the context is reduced but not fully deactivated. This means that the context of an object is useful for object detection under partial occlusion, but it should not have as much weight as the object parts. In summary, we have seen that partial occlusion is a fundamental problem for deep learning systems that needs to be addressed. In our work, we have integrated prior knowledge about compositionality into neural network architectures, and we have observed that this leads to very strong generalization ability beyond the training data in terms of partial occlusion and context variations, while also retaining very high discriminative performance on data that is similarly distributed as the training data. These are references to the papers that I just introduced and that will be presented in the upcoming CVPR main conferences, and the link to the code of the compositional nets for image classifications. Thank you for listening, and I'm happy to take questions.